noche te persigue, entrégate a ella o dile que tienes dolor de cabeza, sobrita de reflejo.
Hi, my name is Anil Nair, and I'm an aerospace engineering student here at UCLA. And I'm going to help you by going over some math concepts and examples. Good luck.
So we're going to go over the formal definition of a derivative. So the derivative is just it's the slope of a function. It's also the rate of change of the function, and it's pretty much a function itself. So if I plug in values, if I have an f of x, for example, and I have the derivative of f, I can plug in values of x to find the slope at each x value. So we can get to a derivative by first starting with the concept of an average rate of change. And the way we can do that is we look at some graph of function f of x. And let's say this is the point in question, we'll call it x. And we know how to find the average slope between x and, let's say, some point called x plus delta x. So there's distance delta x in between them. We wanted to find the slope of the secant line. So this is a secant line. It's pretty easy. This is f of x. This is f of x plus delta x. So slope of this line from x to x plus delta x equals the change in f over change in x. This is essentially f of x plus delta x minus f of x, and this is x plus delta x minus x. That's rise over run. This ends up just being delta x anyway. So slope of the secant line is f of x plus delta x minus f of x. And so if we want to find the slope at x, what we can do is we can make delta x smaller. So let's say we make delta x this small. Now our secant line looks like that. And let's say we make it this small. So first it was like this. Now we're making it this small. Our secant line looks like that. And as we get it closer and closer, our secant line becomes tangent. Now we have a tangent line. So as delta x gets smaller and smaller, or we could say delta x is approaching 0. So our instantaneous slope, and now it's no longer of a secant line, now we have a tangent line. This slope is the limit as delta x approaches 0 of this expression. So of f of x plus delta x minus f of x. And we call this instantaneous slope. Instantaneous just means at that point, at x itself, not between x and some other point. We call this the derivative, and instead of f of x, we write f prime of x. And instead of delta x, to save space, we just write h. H is delta x. H is just one character where delta x is 2, so it's easier to write. And there's other ways to write the derivative. We can write it as f prime of x. We can also write it as y prime or y prime of x. We also use the notation d dx, with the d kind of being analogous to this delta that we use right here. So d dx of f of x, or df dx, or dy dx. These are all valid. And for evaluating at some point c, we find the slope at some point c, we can write f prime of x, y prime of x, and we also use this notation df dx, and we put a line and we write x equals c. So this is df dx at x equals c. So if you want to find the equation to a tangent line, equation to any line is y minus y0 equals m times x minus x0. So finding it at some point x equals c, then our x0 will just be c. We have x minus c. Our y0 will just be y at c, which is f of c. And m is the slope of the function at c, so f prime of c. So if we find f prime of c and f of c, then we can easily get the slope equation for the tangent line. So to find the derivative of a function, it needs to be differentiable. And we don't need to go into the technical details of it. Give you more of an intuitive idea. The function must be smooth, so the slope is continuous. So I'll give you examples of things that are not differentiable. And we use the abbreviation diffball a lot, just to save time. So if it has a sharp corner, for example, something like this, right here, the function isn't differentiable because the slope from this side is not the same as the slope from that side. There's no slope at this point right here. Also, vertical tangents. For example, something like this. Here, the slope is undefined because it's completely vertical. That's an infinite slope. And if the function's discontinuous, then the function's not differentiable. So, for example, if we have a jump discontinuity like this, then it's not differentiable. Or if there's a gap in the function, it's not defined here, then it's not differentiable. If you have a vertical asymptote, then it's not differentiable at that asymptote. So that's pretty much it. So if a function is differentiable, then you know it's continuous. So yeah, that's pretty much it on the formal definition of it.